Millions of data packets navigate vast arrays of servers and fiber optic cables every second. But as networks scale, calculating the exact path through them becomes a massive computational burden. When chaotic data structures intersect, severe topological bottlenecks emerge. Solving these bottlenecks requires precise graph computation. We have to evaluate the specific topological constraints of a network and map them to the correct mathematical data structures and algorithmic paradigms. We approach this through a distinct hierarchy of algorithms. At the baseline, we deploy linear traversals to map out the physical connections within a space. From there, we scale up to greedy paradigms and dynamic programming models, attempting to actively optimize our pathfinding through that established space. Eventually, this progression hits a strict mathematical boundary. We reach a threshold of complexity where deterministic polynomial execution fails entirely, forcing us to abandon the pursuit of an exact, perfect solution. We begin at the baseline with breadth-first search, or BFS. This is a traversal algorithm that visits every node in a graph exactly once, prioritizing the immediate neighbors of a given vertex to expand outward level by level. Analytical, this Q data structure trace demonstrates how that concentric expansion is mechanically enforced. Operating on a strict first-in, first-out processing order, newly discovered neighbors are added to the back of the queue, while the algorithm sequentially processes the nodes waiting at the front. Depth-first search, or DFS, takes the opposite approach. Instead of exploring broadly, its objective is to plunge as deep as possible down a single branch before it hits a dead end and is forced to backtrack. This stack-based trace illustrates how DFS manages that vertical dive. Using a last-in, first-out data structure, the stack actively holds the sequence of previous states, allowing the algorithm to trace its steps backward via sequential pop operations to find the next unexplored path. Both of these methods operate predictably in O of V plus E time. Their execution speed scales linearly relative to the total number of vertices and edges in the graph. BFS and DFS map relational space reliably. They identify exactly what is connected to what. However, they possess no mechanism to optimize that space. They process the physical connections, completely blind to the actual costs of traveling between them. In practical networks, connections carry diverse costs, such as physical distance, latency, or energy consumption. Adding these edge weights transforms the computational objective into finding a minimum spanning tree. A minimum spanning tree, or MST, is a strict configuration. It must connect all the vertices in the graph, it must yield the lowest possible total edge weight, and it must contain zero closed loops, or cycles. To build this, we can deploy Prim's algorithm. This is a vertex-based greedy strategy. Seated at a single starting node, it expands outward by always selecting the absolute cheapest adjacent edge available at that exact moment. Kruskal's algorithm takes an alternate greedy approach. Instead of expanding outward from a single point, it is an edge-based operation. It evaluates the entire network, sorts all edges globally from lightest to heaviest, and adds them sequentially. But Kruskal's contains a mechanical hazard. If an algorithm blindly adds the lowest weight edges across a global space, it will eventually connect two nodes that are already part of the same tree, creating an invalid closed loop. To prevent cycles, Kruskal deploys the union find data structure. This pseudocode details its near-constant time operation. It uses union by rank to attach smaller trees under larger ones, and path compression to point nodes to their root, rejecting edges that share parents. Greedy algorithms are highly efficient, yet their success relies entirely on a fragile assumption that selecting the locally optimal choice at any given step will seamlessly compound into a perfectly optimized global result. That local assumption shatters the moment a topology introduces a negative weight edge. A greedy algorithm evaluating a localized negative cost will make a choice that sabotages the global optimum. To guarantee a single source shortest path in a hostile topology, local optimal assumptions become useless. The system must pivot to dynamic programming. The Bellman-Ford algorithm is the dynamic programming solution specifically built to process networks containing negative weights. This matrix trace tracks Bellman-Ford's core action, edge relaxation. The handwritten conditional statement defines the logic. If the known distance plus the connecting edge's weight is less than the recorded distance to the target, it updates with the new shorter path. Because a negative weight edge could alter a path anywhere in the structure, Bellman-Ford forces this relaxation process across all edges exactly v-1 times to ensure absolute global propagation. After exhausting the network, the algorithm executes one final failsafe, the negative cycle check. If an edge can still be relaxed after that v-1 loop, it proves the graph contains a negative weight cycle. This indicates an infinite optimal loop exists, and calculating a shortest path is mathematically impossible. Dynamic programming trades execution speed for certainty. By abandoning fast, localized choices, it exhaustively processes the data to guarantee a global optimum. Traversals, minimum spanning trees, and Bellman-Ford all share a crucial trait. They are P-class problems. They execute predictably in polynomial time. This Venn diagram maps computational complexity. Class P problems are easy to solve. Class NP problems might be hard to solve, but their solutions can be verified in polynomial time. The overlapping center zone is NP complete, containing the absolute hardest problems in NP. The minimum vertex cover problem sits squarely in this class. The objective is simple: find the absolute smallest set of vertices that touch every single edge in a network. But calculating an exact minimum vertex cover defies polynomial timescaling. As the graph grows, the number of combinations spirals out of control. To process the network, a deterministic global solution must be abandoned entirely. Instead, we deploy a two-approximation polynomial workaround. The algorithm repeatedly picks an uncovered edge and blindly adds both of its endpoints to the set. Measured, this approximation guarantees a solution that is no worse than twice the optimal size. Mathematical exactness is sacrificed to regain polynomial execution speed. Algorithm design goes beyond simply writing instructions. It is the art of recognizing whether a topology requires linear mapping, greedy assumptions, dynamic exhaustion, or a bounded approximation to bypass the very limits of computation itself.